Hello, welcome to the presentation of our paper. It's titled GAN-Leaks, a Taxonomy of Membership Inference Attack Against Generative Models. Over the past few years, generative adversarial networks have shown great improvement in capturing complex data distribution and generating novel samples. A rapid development towards generating high-resolution images without artifacts can be seen in the computer vision domain. Recent works on GANs have also demonstrated great success when applied on privacy-sensitive datasets, such as face images and medical records. However, the corresponding privacy risk is not well studied. In this paper, we investigate membership inference attack against GANs, with which we hope to better understand and control the privacy leakage when deploying GANs. Also, we aim to provide insights for research in the field of privacy-preserving data sharing. In summary, we make the following contributions. First of all, we establish the first taxonomy of membership inference attacks against generative models, which benchmarks future research in this direction. Secondly, we propose our novel attack models for practical settings, which are easy to implement while showing promising results. Moreover, we conduct a systematic analysis of the attack performance, spanning diverse data modalities, model architecture, training configurations, and attack scenarios, etc. Let me first introduce the taxonomy. In short, the taxonomy is proposed based on the type of information accessible to the attacker. In particular, we first distinguish the white box and black box cases, based on whether the attacker can access the model internals or not. And we further categorize the attack scenario based on which GAN components are accessible. Here is a diagram of the standard GAN model. During training, the generator receives latent code as input and tries to generate samples similar to the real data, while the discriminator tries to tell the real and fake data samples apart. After the training is done, new latent code will be sampled from the prior distribution and input to the generator for generating new samples, while the discriminator is no longer useful and will normally be discarded. We then introduce 4 different cases in an increasing order of the amount of knowledge accessible to the attackers. The first one is the full black box case, where only the generated samples are available. This corresponds to the case where a synthetic dataset is released and is a widely adopted setting for dataset sanitization. The second one is the partial black box case, where the input and output of the generator is accessible, but its internals remain hidden from the outside. In this case, the attacker can query the generator and obtain more information by adjusting the queries. The third one is the white box case, where the whole generator is released, with its internal accessible. This is the default setting used for GAN-based differentially private data generation. In the last case, accessible full model. In this case, the whole model is released. However, this setting is less realistic as the discriminator is not used for inference and will not be deployed. Here we summarize all the attack scenarios in the table. In contrast to previous work, which only consider limited or unrealistic settings, we conduct a systematic investigation of all attack scenarios and make a complete comparison to all previous methods. Here we introduce our proposed method. Basically, we formalize the membership inference attack as an optimization problem. Specifically, given a query sample, we find its closest reconstruction by optimizing over the generator's output space and the query sample will be classified as a training sample if it has small reconstruction error. Our objective consists of 3 terms: the element-wise mean of square error, a visual similarity term for image data, as well as a penalty term on the latent code. To tackle the different attack scenarios, our generic model can be easily instantiated to different variants by choosing different optimization methods. However, the reconstruction error is easily affected by the structure in the sample appearance, leading to a false positive for non-member samples with simple structure, and false negative for training samples with complicated structure. For addressing this, we propose attack calibration. Specifically, we train a reference model on a relevant but disjoint dataset, and we calibrate the reconstruction error by taking the difference on the victim model and on the reference model. We show our simple attack calibration technique consistently improve the attack performance across all different cases in practice, and we also prove it's near optimal under a Bayesian perspective in theory. More details can be found in our paper. We conduct extensive experiments for better understanding the privacy risk related to GAN deployment. In particular, we investigate 3 datasets with diverse modalities, 5 different GAN models, 2 baseline methods, and we also perform a systematic analysis spanning several orthogonal directions. We will be presenting selected results here. Please refer to our paper for all the analysis. Here we demonstrate results on medical dataset when we change the size of the training set. We would like to highlight that the attack is highly effective when the training set is not sufficiently large. This indicates extremely high privacy risk when applying GANs on medical dataset, which typically has very limited samples. Here we show the attack performance on face dataset when considering all different attack scenarios as well as victim model architectures. We notice that previous works are either less effective in the restricted cases or under less realistic assumption. In contrast, we highlight that our attacks are still effective in practical settings and even outperforms previous methods with less realistic assumptions. More details can be found in our paper, which include a detailed discussion of possible applications in different attack scenarios and related research topics in the taxonomy section, and more technical details about our proposed attack models. And we will also provide more experiment results that investigate different training configurations, the attack calibration, and possible defense mechanisms. Our source code and models are published on GitHub in order to promote reproducible research in this domain. Thanks for your attention.